In video lecture 2, we're going to learn about set operations, which are ways of creating new sets from old ones. To begin with, the most basic set operations are those of union and intersection. If you have two sets, x and y, then their union, which is written like this with a cup symbol or a U, is the set of things which are in x or in y, or both. So mathematical or is always inclusive. We include in the union things are in x and things which are in y and things which are in both x and y. The intersection, on the other hand, of x and y is written like this with an N-shaped symbol, and it means the set of all things which are both in x and in y. Here are a couple of examples. If we take 1, 2, union 2, 3, then that's the set 1, 2, and 3. That consists of the set of all things which are either in the set 1, 2 or the set 2, 3. And again, mathematical OR is inclusive, so things like 2, which are in both of those sets, are elements of the union. On the other hand, if we take the intersection of 1, 2 and 2, 3, then that's just the set containing 2, because 2 is the only element in common between those two sets. If we take the intersection of 1, 2 and 3, 4, well, there are no things which are in the set 1, 2 and in the set 3, 4. Therefore, their intersection is the empty set. It has no elements. You may also hear some alternative terminology for union and intersection. The union is sometimes called the join of two sets, and the intersection is sometimes called the meet of the two sets. This is rare, but you might just hear that somewhere. Here are two more set operations, the difference and the complement. The difference of x and y, sometimes called the set difference, is written like this with a backslash or a set minus, and it's defined to be the set of things which are in x but which are not in y. You'll sometimes hear that pronounced as x take y, or the difference between x and y. If you have a set x which is a subset of a larger set omega, then the complement of x in omega is defined to be the set difference of x and omega, and it's written as an x with a superscript c. So here are some examples of that. If you have the set 1, 2 and the set 2, 3, and you take their difference, then that's the set of things which are in 1, 2, but which are not in 2, 3. So we have to throw out 2 if it's in there, and throw out 3 if it's in there. The result is just the set containing 1. On the other hand, if we take the set difference 1, 2, take 3, 4, then that would be simply 1, 2 again, because neither 3 nor 4 is an element of the set containing only 1 and 2. For complements, if we take omega to be the set of natural numbers, so remember in 0007 that's the set 0, 1, 2, 3 and so on, and if x is the set containing 1 and 2, then the complement of x in omega, that's the set difference of omega and x, so omega take x. So we simply take the elements of x and throw them out of omega, and what we're left with is 0, 3, 4, 5, 6, and so on. It's quite common to draw Venn diagrams for all of these set operations. So I'll draw diagrams of the 4 operations we've met so far. If you have a set x, then in a Venn diagram you represent this by a blob or a circle, and the elements of x are supposed to be the things inside the circle. So sometimes we will draw dots to represent the things inside x, and sometimes we simply think of the elements of x as being the area inside the blob. Well, if we then draw another set y, which might or might not intersect with x, then the union is the set of all things inside either of those two blobs, so the combined area of both blobs, which I will shade in like this, so the entire area. That then is x union y. If we look at x intersection y, well, that's the area in common between those two sets. So here is x and here is y, and this time the overlap between them would be x intersect y. Let's draw the same diagram again, a set x and a set y. This time the difference is all the things which are in x but not in y. So what we need to do here is to cover all the things which are in x but not in y. So this would be x take y. Finally, we need to illustrate the complement. So when we talk about the complement, usually we're thinking of some kind of big universe of sets which contains all of the sets we're talking about. So all of the sets we're talking about will be subsets of this big set omega. That's why we use the word omega, because it's the last letter in the Greek alphabet, so it's somehow the ultimate, the biggest thing. So when we draw diagrams of complements, we'll often draw the omega as a big set, a rectangle containing everything else. And then inside it will be whatever other sets we were talking about. So here, x. An x complement will be all the things which are outside x. So everything which lies outside our set. So in green, that's x complement, which is, by definition, omega set minus x. Okay, those Venn diagrams are often quite useful for thinking about equalities of sets. If you're not quite sure whether one complicated expression involving unions and intersections and complements is equal to another, it can be helpful just to draw diagrams of these things and see whether they look visually the same. Next definition is the cardinality, or the size of a set. What that means is the number of distinct elements in the set. And the word distinct is important here. It means how many different elements there are in the set. So you have to be careful because, as we know, sets ignore repetition. You can have a set like 1, 1. That's a perfectly legitimate set. But its size is not 2. Its size is 1 because it's only got one different element, namely the number 1. So here are some more examples of the size of sets. The size of the empty set is 0. It has no elements at all. The size of the set 1, 2, 3 is 3. There are 3 different elements, 1, 2, and 3. And finally, the set of 3, 2, 1, 2. Again, this is a little bit of a trick question because the number of distinct elements is 3 because the number 2 is appearing twice there. So let's just emphasize this. Distinct elements. That's important. So there are two basic possibilities for the cardinality of a set. It can be finite or infinite. A set is finite if its size is a natural number, so 0, 1, 2, 3, 4, and so on, and infinite if it's not finite. As an example, the set 1, 2, 3, that's finite because it has 3 elements. The empty set, that's finite because it has 0 elements. The set 1, 2, 3, 4, 5, 6, 7 up to 10 to the power 10, or 10 to the power 10 to the power 10, or 10 to the power 10 to the power 10 to the power 10. All of those things are finite sets because they have only a natural number of elements. On the other hand, the natural numbers themselves are an infinite set because there are infinitely many different things. The number of different natural numbers is not a natural number. The real numbers are an infinite set. The set of prime numbers, perhaps you've seen a proof of this, is also an infinite set. There are more prime numbers than any natural number, and there is standard proof of this, which you've probably seen. Goes by proving that if you give me any natural number, I can find more prime numbers than that natural number, which proves exactly that the size of the set of prime numbers is not a natural number. There are infinitely many different primes.